All right, let's dive right in. Today, we're tackling a massive question. How can we get computers to mimic the single most powerful processor out there, the human brain?
I mean, think about it. What if computers could do more than just follow a set of instructions? What if they could actually learn from experience, spot patterns, and even predict what's coming next, just like you and I do? This isn't some far-off sci-fi concept. It's the real idea at the heart of what we're talking about today.
The answer to that question is something called an artificial neural network, or ANN for short. And it's exactly what it sounds like, a computer model that's directly inspired by the wiring of our own brains. Now, the goal here isn't to create a thinking, feeling machine, not at all. It's about borrowing the incredibly smart and efficient design that nature already came up with for learning and handling information. Okay, so let's get a little more specific. In your brain, a neuron gets signals, thinks about them, and then fires off its own signal. Well, an artificial neuron does basically the same thing. It takes in some numbers as input, but here's the cool part. It multiplies each input by a weight, which is just a way of deciding how important that piece of information is. Then, something called an activation function makes the final call on what the output should be. It's really just a simple, math-based version of what's happening in our heads all the time.
So you might be asking, why bother with all this? Well, because the brain's design is just brilliant. It gives us some huge advantages. For one, neural networks can do a ton of calculations all at once, which makes them super fast. They're also really tough. You know how our brains can keep working even if some cells aren't perfect? Same idea. If a small part of a neural net gets damaged, the whole thing doesn't just crash. But here's the real superpower. They can look at messy, incomplete, or just plain noisy data and still figure out what's going on. That's a total game changer.
Okay, so we've built these things that look kind of like brains, but how do they actually learn? It's not magic, I promise. It really boils down to two main approaches. You can think of it as learning with a teacher or learning all on your own.
So let's break down those two styles. First up is supervised learning. This is where we play the role of the teacher. We give the network labeled data. Basically, here's the problem and here's the right answer. On the other hand, you have unsupervised learning. Here, we just dump a whole bunch of data on the network and say, go figure it out. The goal is for it to find hidden patterns all by itself. Let's dive a little deeper into supervised learning. Imagine you're teaching a kid what a cat is. You show them a picture of a cat, and you say, cat. You show them a picture of a dog, and you say, not a cat. It's the same idea for the network. It gets an input, it makes a guess, and we tell it the correct answer. That's the target. The network then looks at how wrong it was, that's the error, and it tweaks its internal settings just a little bit to do better next time. It does this over and over, sometimes millions of times, until its guesses are really, really good.
Now, unsupervised learning is totally different. It's less like being in a classroom and more like being a detective. The network gets a massive pile of data, let's say a bunch of customer shopping habits, but with no labels, no answers. Its job is to sift through all that information and find natural groups or clusters on its own. For instance, it might discover that there's a group of people who always buy coffee and books together without anyone ever telling it to look for that connection. It's all about pure pattern discovery. All right, so if we focus back on that supervised, learning with a teacher method, there's one particular type of network that absolutely dominates the field. It's famous for being incredibly powerful, but also for being, well, a bit of a mystery. We often call it a black box, and its name is the multi-layer perception.
So what makes this thing tick? The key is right in the name, multi-layer. An MLP isn't just a simple input and output system. It has an input layer, an output layer, and, this is the crucial part, one or more hidden layers of neurons tucked in the middle. And those hidden layers are where all the heavy lifting happens. They're what allow the network to solve really complex problems, the kind where the data isn't neatly separated. A single layer of neurons? No way. It just can't do that kind of complex work.
So how does an MLP actually learn? It uses a really clever algorithm called backpropagation. Think of it like a two-step dance. Step one is the forward part. An input goes all the way through the network, from the first layer to the last, and pops out as a guess. Then comes step two, the back part. The network figures out how wrong its guess was, and it sends that error signal backwards through the network, tweaking all the connections along the way to be a little bit better next time. And it just repeats this forward and backward dance over and over and over again until it gets really accurate.
But, and this is a big but, all of this power comes with a serious downside. We call these things black boxes for a reason. An MLP can give you an incredibly accurate answer, but good luck trying to figure out how it got there. The why behind its decision is spread out across thousands or millions of tiny adjustments in a way that's just not understandable to a human brain. It works, but we don't always know why.
And that black box problem? It's a huge deal. I mean, think about using this for a medical diagnosis or for a bank loan. You need to be able to trust and understand the decision, right? So it raises a really important question. Is it possible to have the power of a neural network, but without the mystery? Can we have transparency?
Well, that's where something called a Radial Basis Function network, or RBF network, comes into the picture. It's a totally different design, built from the ground up to be more understandable. The big difference is in its hidden layer. Instead of just doing calculations, its neurons work more like proximity sensors. Each one is tuned to a specific center point, and it activates based on how close a new piece of data is to that point.
And this creates a really fundamental difference in how they think. An MLP is what we'd call global. Pretty much every neuron has a little bit of a say in the final answer, which is what makes it so hard to interpret. But an RBF network is local. Each hidden neuron is like a specialist, an expert on just one little part of the data. This makes their logic way easier to trace and understand.
So how does that actually work in practice? Well, that hidden layer in an RBF network is special. Each neuron in there becomes a prototype for a specific type of data. It's like having a collection of perfect examples. So when new information comes in, the network makes its decision based on how similar that new info is to each of those prototypes. You can literally look inside and say, okay, it made this choice because the input was a 90% match for prototype A, but only a 10% match for prototype B. It's a process you can actually follow.
All right, we have covered a ton of ground here. We went from the human brain all the way down to the nuts and bolts of different network designs. But why does any of this matter? Why is this distinction between a black box and a more open system so important?
Let's just quickly recap. We started with the idea that ANNs are models inspired by our own brains that learn from data. We learned that they can do this with a teacher, which is supervised learning, or they can figure things out on their own, which is unsupervised. From there, we talked about the super powerful MLP, the workhorse of AI, but one that's often a complete black box. And that's exactly why alternatives, like the RBF network, are getting so much attention. They offer a path to getting powerful results in a way that we can actually look at, understand, and, most importantly, trust.
And really, this all leads to a huge, critical question for all of us. As these incredibly powerful tools get woven into everything, from our healthcare to our finances to our transportation, we're constantly going to face this trade-off. How much do we rely on a black box, even if it's right most of the time? The biggest challenge going forward isn't just about making these networks more powerful. It's about balancing that power with our very human need to understand why a decision was made. It's about power versus transparency.
And that's our deep dive into the artificial brain. Hey, if we managed to make that black box a little less mysterious for you, do us a favor and hit that like button. Share this with someone and subscribe for more explainers just like this one. Thanks for tuning in.